Nikhil and Vinod for the kind invitation. So this is work on, the title on the website is the observability and controllability of linear dynamical systems under sparsity constraints. And when I talk about this to people, the typical reaction is, so what's new here? Hasn't this topic been studied to death already? And then I say, okay, so who has, where has this been studied? And then people are a little more stumped on being able to point me to references on this topic. So maybe I'd like to take a short minute to first tell you how we arrived at this problem. A couple of years ago, I attended a talk by Professor P.R. Kumar from Texas A&M University, where he was talking about actually, if you don't mind, I'll remove the mic because the echo is very disturbing. I don't know if you had that thing for the recording. Okay. Okay. I guess I hear an echo in my ear, a little bit delayed, and it's quite disturbing. Hello? Yeah, it's a little better. Okay, so I attended a talk by Professor P.R. Kumar where he talked about cyber-physical systems and secure controllability of cyber-physical systems, in which he modeled an attack on a cyber-physical system using a sparse attack where an agent manipulates some actuators or sensors in the network and thereby tries to drive the system into an undesired state. And the system evolution itself was described by a classical linear dynamical system model. Yeah, that's much better, thank you. And that sort of got me thinking about how one does sparse control and observability of more general linear dynamical systems under these sparsity constraints. This is joint work with my former PhD student Geethu Joseph and Chandrasekhar, who's here in the audience. Both of them, really brilliant students who have done all of this work. So I'll start. So basically, first let me tell a few words about compressed sensing. It deals with this very well understood problem of how you recover sparse vectors using linear measurements. And the key aspects that one looks at in compressed sensing are issues of uniqueness, algorithms that can recover these sparse vectors with relatively low complexity, and guarantees, that is, how many measurements are required to be able to recover these sparse vectors. As I will show you a little later in the talk, the kind of questions that arise in the use of sparsity or linear dynamical systems under sparsity constraints actually ask fundamentally somewhat different questions compared to these three questions that are asked in compressed sensing. So this is the focus of the talk, is to translate compressed sensing results to linear dynamical systems under sparsity constraints. So here is the basic linear dynamical system. You have the system state, which is represented by xk. It evolves as axk minus 1 plus buk. This is the state at time k minus 1, and uk is an external input that's applied on the system. And b is called the input matrix, and a is typically called the state transition or the transfer matrix. Then you also get observations yk, which is, in this case, I have represented it as ck times xk. So ck could be time varying plus wk. So in this model, we are going to assume that a, b, and ck are all known. And we will worry about trying to estimate the state of the system, that is this part, as well as the design of these control inputs to drive the system to a certain desired state. Now, when we look at the problem of estimating the state of the system, we will consider a scenario where there is some time zero at which we somehow know that the system state is sparse. And this kind of problems arise in problems related to epidemic spreading, pollution, virus spreading, and so on, where there are a small number of origins of this virus or epidemic, and that spreads out over time and infects every part of the system. But there is a time zero where the state is sparse or relatively sparse, and you can use those times to try and exploit the sparsity to estimate the state with fewer number of measurements compared to what would be required if you didn't have this sparsity constraint. And the imposition of sparsity on the control inputs arise in a variety of problems related to energy-aware scheduling of actuators, where these actuators could be running on batteries, and you don't want to utilize these actuators too heavily, so you want to at each point in time use a subset of those actuators so that you conserve the battery energy on these actuators and improve the network lifetime. And there are other examples also. So we'll talk about observing the initial state of the system, that is the state at time 0, and controllability of the system using sparse inputs, and the feasibility of staying in a given state using sparse inputs. Okay, so we'll start with observability. So if I simply stack, okay, first of all, when you're looking at the problem of observability, you can, without loss of generality, consider the inputs to be equal to 0. That's because you can just subtract whatever is BUK from each YK, and so you can stack the YKs one below the other to get a big vector Y, which is of size km cross 1. So each of these observations are of size m by 1. So when you stack k of them together, you have a vector of size km by 1, which when you stack all these measurement matrices one on top of the other, you get this equivalent measurement matrix, which we denote by O, which is of size km by n. N is the length of this vector. That is a vector at the initial vector at time 0. And so this is an equivalent system of measurements. Y is equal to O times x0. And in the classical case, if x0 is not sparse, you impose no constraints on x0. You just need O to be of rank n, which means that km must be of the order n. So now we are saying that we have this a priori knowledge somehow that x0 has at most s non-zero entries. So does this extra information allow you to observe the system state with fewer number of measurements? So the one thing I'll mention is that this, already you can see that this exactly looks like a compressed sensing equation. The one difference is that the measurement matrix here is of this form. It's C0a, C1a, Ck minus 1, a to the k minus 1. So this is not a sort of typical measurement matrix that is used in compressed sensing, which generally assumes that the entries of the sensing matrix are IID sub-Gaussian or something like that. So so in that way, this problem is somewhat different from the classical compressed sensing type setup. So, the main result that we will use is this classical result from CS, which says that if the restricted isometry constant of the measurement matrix is smaller than some delta, which is a number that is specified by your favorite algorithm that you use for recovery, then the standard compressed sensing algorithms will succeed. So for example, for L1 recovery, delta could be like 1 over 3 or, 1 over 3. The approach we follow is to do a restricted isometry property analysis of this structured sensing matrix O, and then find how many measurements are, use that to bound the number of measurements that ensures the RIC bound holds. So basically, these give us a sufficient number of measurements. That is, if you have this many number of measurements, your sparse recovery will be successful. So typically, so one other thing is that if these matrices A are all are a scaled unitary matrix, then it is already known that if what you require is Km to be of the order S log n over S, and that is sufficient for you to be able to recover a sparse x0 from Y. But what happens is if these CKs have independent Gaussian entries, then right multiplication by a unitary matrix doesn't change its distribution. So the analysis actually directly follows. The overall matrix is also Gaussian, and so all you require is Km to be of the order S log n over S. So if A is not a scaled unitary matrix but arbitrary, it's the system transfer matrix, so it's not necessarily going to be unitary. So what property of A affects this recoverability of x0 from this system of equations? Turns out the answer is actually the condition, it depends on the condition number. At least this is a sufficient condition. So it's possible there are other ways to look at the recoverability, but the one result we have here, it depends on the inverse of the condition number. So basically we have done this kind of a restricted isometry property analysis of this structured random matrix. The difference, as I mentioned, is that these are, if I assume that the Ci's are sub-Gaussian, then it is the sub-Gaussian matrices with the rows multiplied by different arbitrary matrices. And that is specifically by the powers of A. We've considered both cases, one where the CKs are independent matrices, and the other case where CKs are all identical but equal to, or one of them is equal to, it has a IID sub-Gaussian entries. So the result looks like this. It's a sort of big equation, but it's easy to parse the equation. It says that if Km times something exceeds C times S log n over S plus a constant that depends on the failure probability you want to guarantee, then the restricted isometry constant of the resulting matrix is going to be smaller than delta with probability close to 1. And this particular factor here is the target delta that you're targeting here for the restricted isometry constant minus 1 plus lambda to the 2k minus 1, where lambda is the inverse condition number of matrix A. So for example, if the matrix is well conditioned, that is, for instance, if A is a unitary matrix, then lambda is equal to 1. So this becomes delta squared. So it just says Km times delta squared should be of the order S log n over S, and that ensures successful recovery of the sparse initial state. On the other hand, if A is poorly conditioned, then its condition number is going to be large, inverse condition number is going to be small, and so you need this kind of, so that only adds a smaller number here, which means that this overall number of measurements required is going to be larger. So I'm not walking you through the proof of this result. It's a little bit technical and long, but I can discuss that offline if there is interest. So to summarize, basically, if the state is non-sparse, you need Km. K is the number of observation vectors you collect, and M is the size of each of those vectors. If Km is of the order n, you will be able to recover the state, irrespective of whether it's sparse or not. If it is sparse and A is unitary, Km should be of the order S log n over S. What we have shown is that if the state is sparse and the measurement matrix is time varying, meaning that each of those observation matrices have IID sub-Gaussian entries, then Km needs to be of the order S log n over S. Whereas if it is sparse and time invariant, you have a slightly larger log factors that you pick up, and the number of measurements needed is S log squared S times log squared n. So we've also extended this to the joint recovery of the sparse initial state and sparse inputs. So for instance, if there's a system that's been driven by sparse inputs, but the inputs are unknown, then you may want to recover not only the initial state, but also the inputs that were applied. So that way you know the entire evolution of the system by just looking at the observations. And so there is also the extension to that in the longer version of the paper. And these results are generally stronger and more general than other results that are there in the literature. So next I'll talk about controllability. So again, the evolution model is that xk is equal to A times xk minus 1 plus buk. And the question that we ask here in controllability of a linear dynamical system is, can we drive the system from an initial state x0 to x init to a final state x final for any pair x init x final using only sparse inputs? That is, each input vector uk should have an L0 norm at most S. So if I stack these equations one on top of the other, I get this equivalent system of equations. Xk minus A to the k x0 is equal to this horizontal stacking of these matrices times this sequence of input vectors u1 through uk that were applied to the system. So since each of these UKs are at most S sparse, this subvector has a sparsity S, this subvector has a sparsity S, and the last subvector also has a sparsity S. So this is equivalent to a problem where you're looking for a piecewise sparse solution to this system of linear equations. And so there are some algorithms in the compressed sensing literature that will give you, that will output piecewise sparse vectors. For example, you can imagine a very simple modification of the orthogonal matching pursuit, where in the OMP algorithm, each time you're selecting a column that is most correlated with your output, that is xk minus a to the k x naught. And as soon as you select more than s columns within each of any one of these groups, then you remove that entire group from the sensing matrix, and then you proceed with the OMP algorithm with the remaining set of columns. So if you do that, you can arrive at a set of vectors that will satisfy the constraint that the L0 norm of UK is at most S, and if the residual goes to 0, then you have solved this system of equations. However, okay, before I go there, I just want to mention one small thing here, that the question we are asking here is actually slightly different from the type of questions that are typically asked in sparse signal recovery. In sparse signal recovery, you start by assuming that your observations were generated by multiplying a sparse vector by a sensing matrix, and then you're asking, is that solution, if you were to try to look for the sparsest solution to this system of equations, is it unique? Is there a fast algorithm that will find it? And what guarantees can I give about such algorithms? Whereas here, the question is slightly different. It's the question of, does there exist a piecewise sparse vector that satisfies this system of linear equations? So it's a somewhat different flavor of a question. In the case where you don't have a sparsity constraint, so that none of these vectors need to be, the UIs need not be S-sparse, they can be arbitrary. In that case, there are two equivalent tests that are well known in the literature. These are very classical results. The first is called a Kalman rank test, which says that if this matrix A to the n minus 1b, A to the n minus 2b, all the way down to b, this stacking of all these matrices together, if that has a rank equal to n, then this is an if and only if condition for controllability of this system. And a similar or a related test is this is also an if and only if test, which is called a PBH test, which says that for all lambda in complex valued lambda, the matrix A minus lambda I B must have a rank equal to n. So when either of these conditions are satisfied, then the system will be controllable. So in the sparse case, one can immediately see that the direct extension of this Kalman rank test, which we call a Kalman rank type test, is that there should exist some k less than infinity and a set of sets Si, I equal to 1 to k, such that each of these is at most has at most S entries, so that when you take this matrix which has AK minus 1 BS1, BS1 is the submatrix of B with containing columns indexed by S1, AK minus 2, BS2, etc. up to BSK minus 1, this has to have a rank equal to n. And an equivalent of this PBH test for the case where these inputs are restricted to be sparse is unknown. But the disadvantage of a test of this nature is that it's combinatorial in complexity, and of course you have to compute. This is for, there exists a case, so potentially you have to compute very large powers of A, and there could be numerical issues with doing that. So first of all, some necessary conditions on sparse controllability. One thing is that if a system is sparse controllable, then it is certainly also controllable, which means that the PBH test must succeed. If the PBH test succeeds, it also means that the Kalman rank type test will succeed. That means there exists a K and a Si such that this matrix has a rank n. In turn, this implies that since these are all just linear combinations of, the rank of this, each of these are linear combinations. When I multiply A power K minus 1 times BS1, I just get a linear combination of the columns of A. So for this to happen, this matrix has to have a rank equal to n. Now this has only at most s columns. So this will happen only if rank of A plus S is greater than or equal to n. So the necessary conditions are that first of all, this first condition here, which is simply the PBH test saying that the system must be controllable, and secondly, S should be at least equal to n minus rank of A. So these are necessary conditions for sparse controllability. And it turns out that these are also sufficient. How much time I have? Okay, 10 more minutes. So I can maybe briefly indicate how one shows that. So for sufficiency, start by saying that suppose the Kalman rank type test fails. If that fails, we want to show that one of those conditions, these two conditions that I showed you in the previous slide, will be violated. If it fails, then it means that if I take any set Si like this and a k hat number of such sets, and specifically I'll choose these sets such that together they cover all the columns of this B matrix. Then when I stack this matrix together, and now this is a kind of, what I'm considering is a very large number of possible inputs that I apply. Since it's uncontrollable, it remains uncontrollable no matter how many inputs I apply, which means that this matrix, which is obtained by stacking k tilde times, or k hat, k tilde times n such such matrices together, this will still have a rank which is strictly less than n. Now, if I take this matrix here, so what this is doing is it's saying I'll apply inputs whose support is S1 for n time instance. Then I'll apply inputs whose support is S2 for the next n time instance, all the way down. And here there's, I'll use Sk for the last n time instance here. So if I just simply rearrange the columns of this matrix, I can have all these matrices which have a to the n minus 1 that is common to them, and I stack the remaining matrices together. I call that the B tilde matrix, or B tilde star matrix. Then a to the n minus 1 B tilde star, a to the n minus 2 B tilde star, all the way down to B tilde star. This matrix has a rank which is strictly less than n. So that's what we just saw. Now this is basically the Kalman rank test for an unconstrained system whose transfer matrix is A and the input matrix is B tilde. So the Kalman rank test for such an unconstrained system is failing, which means that the PBH test will also fail because both are if and only if tests, which in turn means that there exists a lambda and a non-zero vector z such that A minus lambda I and B tilde star, when I stack them together, it has a rank less than n, which means that lambda transpose A is equal to lambda z transpose. So z transpose is a left eigenvector of A, and z transpose B tilde star must be equal to 0. So if you substitute for B tilde star, since B tilde star has powers of A in it, you can write this as z transpose times these lambdas multiplied by the corresponding columns of B. But I chose these S1 through Sk tilde such that these columns together contain all the columns of B. So if Z transpose times B is equal to 0, it means that, so for this to happen, either Z transpose B itself is 0, which means that this matrix lambda A minus lambda I, since it has a non-zero eigenvector corresponding to which this has eigenvalue equal to 0, the rank of this matrix itself is strictly less than 1, so condition fails. And similarly, if lambda is not equal to 0, this is what happens. If lambda equals 0, then you have Z transpose times B Sk tilde is equal to 0, which also again implies that this matrix has a rank strictly less than n, so the condition 2 of the necessary conditions will fail. So if that's a little technical, don't worry about it. The point is that the two conditions I showed you in the previous slide, which is these two conditions here. First of all, for all lambda, the rank of this matrix must be equal to n, and then n must be smaller than or equal to S plus rank of A. These two conditions are both necessary and sufficient for sparse controllability of the system. So we have several other results we came up with, including bounds on the minimum number of input vectors to guarantee sparse controllability. They take this form. Essentially, the point is to try and understand how sparsity affects how many control inputs are required to steer the system to a desired state. And of course, from the fact that this thing arises in the denominator, you can see that if I allow less sparse vector, or I increase the value of S, the number of inputs that I'll need to apply actually decreases, and it is at most N. N is the dimension of the state, and this upper bound is also the upper bound on the unconstrained system. So in some sense, at least in terms of the upper bound, you pay no penalty for insisting on sparse input vectors. But in the lower bound could become larger because if you are restricted to using sparse vectors. The lower bound is simply the minimum of these two things. The rank of B part is there even for the unconstrained system. And further, we have a decomposition type procedure that separates the state space into sparse-controllable, sparse-uncontrollable, and uncontrollable states. This is a very natural decomposition of the linear dynamical system to understand what parts of the system state would be controllable using sparse inputs and what will not. Okay. Finally, I just want to, I guess I am out of time, but I just want to make one or two remarks about staying in a desired state using sparse control. So the objective here is to, if you have a final desired state, you want to apply sparse inputs so that the system stays in that state. So that is equivalent to asking whether this particular problem has a sparse solution. And if the system is asymptotically stable, that is the spectral radius of A is strictly less than 1, what we can show is that for any eta greater than 0, and so suppose you are able to solve this system of equations approximately so that the L2 norm of the error between these two, you are able to find a sparse vector such that the L2 norm is at most delta, then there exists K0 less than infinity such that beyond K0, if you go on applying this input U, the error between this x final and xk is at most delta times some constant plus eta. So you will stay within this much error of the, so my time is up almost. You will stay within this upper bound of the final state for all time. So to conclude, our goal in studying this problem was to connect compress sensing results to linear dynamical systems, and specifically to other different types of problems that arise in control theory. We looked at the observability of sparse initial state, and systems that are unobservable using classical control theory could become observable under sparsity constraints. And we also looked at controllability using sparse inputs, low complexity verification procedures for controllability, and also I briefly alluded to the problem of staying in a desired state. And so there are other open problems such as how do you extend this to other linear stochastic systems, and what if there are energy constraints on the control input in addition to sparsity constraints. So with that, I'll conclude. Thank you very much for your time. Thank you.